K8BYP in a video on what's commonly referred to as a filter capacitor. I'm going to show you that that's a mistaken term, that what's happening is not filtering. This is part of the schematic from the Hewlett-Packard 8660 RF generator, A4 reference VCO assembly with plus 20 and minus 10 volt sources coming in, and what we normally hear called filter capacitors. Capacitors in power supplies are called filter capacitors. And they're called that because if they're not there, then AC ripple voltage might appear on the line, and if we add these capacitors, that ripple disappears, and we think that's filtering. We have filtered out the ripple, and that is completely false. That is not what is happening. Interestingly enough, in the case of these two sources, these capacitors actually are part of a filter. But if you'll notice, L1, L3, C3 is a T network, which in some of my other matching videos I've shown is a resistive matching network. Why in the world would that be in a power supply? And L2C4 is a low-pass L network, again for resistive matching. Why would that be there? It's a DC supply. Why would we want to match a DC supply to a DC supply? That doesn't seem to make any sense. Well, they're there to be frequency selective. The lower one is a better low pass than just a capacitor with a inductor in series. And L1, L3, C3 is typical for RF power amplifiers. The Drake TR3 has a similar setup that also then has another capacitor that would be on the right of where L3 is going to the plate, to the inductor that is before the plates of the amplifier tubes. Zooming out, these circuits use, amplify, generate RF. See a 10 picofarad varicap diode L4 tapped. That's an RF circuit called a VCO oscillator. That circuit uses current. Universally in circuit design, we rely on fixed, stable, so-called filtered voltages because it's easy to measure those. We just take a voltmeter and measure something. It's much more difficult to measure current. To measure the current to or from the base of Q3, we have to break the base and put an ammeter in series, or put a small value so-called shunt resistor in series and measure voltage across it, which is again measuring voltage. But the current varies at an RF rate, and we don't see that. It's hidden. When we do circuit design, we have to start chasing these AC currents around because that's what's really happening. Note these capacitors are at the load, at whatever uses the current. And what they are is not a filter to take something out. They're a local reservoir for current to supply the RF current to the oscillator. It's there and not at the bulk 20 volt supply 6, 8, 10 inches or a foot away, because if it wasn't for these components here, then these RF currents would be drawn over that length of wiring. That wiring has impedance. Those wires are inductors that would set up RF magnetic fields around the power supply wires and cause all kinds of interference. But it is not correct that these are filtering anything out. These capacitors in particular are what I refer to as a local reservoir of current. Now if we look here, 6.8 microfarad, 22 microfarad. I know it's not marked on the schematic, but that's what they are. Symbols for electrolytics. And that's the A4 assembly reference oscillator. But I've just taken the cover off the A4A3 And golly, we don't see any big so-called filter capacitors in there. And this is obviously a rather sensitive RF assembly, because see all the huge ground plane area on top of the board? That suggests a board that's operating at RF. And probably small low-level signals, hence the very heavy shielding. There are no so-called filter capacitors in here to change. That might seem to be a contradiction. If it's such a sensitive circuit, wouldn't we want more filtering? No, because it's not filtering. In a low-level circuit like this that draws small amounts of energy, we use a small capacitor because it holds a smaller charge to supply a higher impedance circuit that doesn't need as much energy. And believe it or not, the so-called filter capacitor for this entire board is not that big one. That's obviously a dipped silver mica. Those are generally in the picofarad range. The capacitor that so-called filters this whole board is that little disc ceramic right there. It's one of the smaller components on the board. But see, it doesn't take much energy to supply this board, so this doesn't have to store much. And that is a 4A3C1 right there, a 0.01. Now that's coming from A4A4, 20 volt, coming from right there, 9, 20 volts coming in, 20 megahertz amplifier going right there. So all it needs to do is supply current that is sourced over a relatively short piece of wire. And it's probably that red wire right there that's going right over into this assembly. So we often see, especially in digital circuits, we see it's common for a designer to sprinkle 0.1 microfarad capacitors everywhere on every IC. That's a wrong approach. The value of those capacitors can be calculated. It's not that hard. Q equals CV, the amount of charge, capacitance times voltage. Know the amount of energy that IC draws per second, and make that local reservoir of energy able to source more than that, so that the current is not being drawn from the external power supply. And it's a simple application, simple calculation. But that is why several board assemblies in this unit have no so-called electrolytic or tantalum filters. They don't need them, because those are there to supply assemblies that have a higher current demand. So there's a skinny on the design with so-called filter capacitors. K8BYP did it.